Right. The time is here. I see the light, so we have to finish discussing about first order ODEs if my computer behaves, okay? All right. So today I'm going to try to cover some little topics here and there, okay? And in some sense, first order ODEs, initial value problems, are way more important than second order or third order or fourth order, because all dynamical systems, right, they are first order ODEs. The Navier-Stokes equations, you know. Okay, you may say wave equations are second order, so we will actually discuss those later on, but most dynamical systems are first order. And actually even second order systems, a lot of times are solved by writing them a system of two first order equations or many first order equations. We are going to spend actually a week to discuss about system of ODEs. All right, so let me start today by discussing a little bit the differences between linear and nonlinear ODEs, right? We mixed them. We did some methods work for some problems, they don't work for others. So we need to see what the differences are between linear and nonlinear ODEs. So the first thing I'm going to remind you, this is what we're looking, right? An equation that looks like this. Y prime equal f, which is a function of t and y. And if this function is a nonlinear function, all right, then we call this a nonlinear ODE. And obviously, if the equation becomes nonlinear, lots of strange things may happen. And some of those strange things you cannot really generalize and say, for any nonlinear ODE, this is what happens. No, it depends on that particular ODE. So the things that, let me just put them up, okay? There are three major differences between linear and nonlinear first order ODEs. So one of them that I will discuss briefly today is that the theory that describes the existence and uniqueness of solutions is very different for the two problems. So if you have a linear problem versus a nonlinear, actually for many nonlinear problems, you cannot even say much about existence and uniqueness. You give up, basically, okay? But maybe for first order equations, there is a very elegant theory that goes behind it, and I will try to briefly discuss it today. You remember when we, looking at the second item, when we discuss about linear equations, in many simple problems, we computed the general solution in terms of some constant terms. We said like constant times c to the minus x plus another constant times x plus something else, right? So effectively, the general solution involves some constants, and every solution basically was differing by what numbers we put in these constants, and that will depend on the initial conditions, okay? However, for nonlinear problems, even if you find the general solution in terms of some constants, it is possible that there is another solution that you cannot get it from the general solution regardless what constant coefficients you put in. You understand? The point is, this concept of having a general solution may not exist for nonlinear problems. So you may have one general solution here that gives you a whole class of solutions, and you may have this other weird solution that doesn't fit in. It comes on its own, okay? And the third item, you remember when we did both linear and nonlinear ODEs, right? We derived some solutions that they were explicit. Remind me, what do I mean explicit? Y equal to this function of t, okay? So in many problems, that's what we got. In some other problems, the solution was actually like maybe y squared minus 5y equal to e to the power t. So it was a quadratic equation that you can actually solve it, okay? So this still was an explicit equation. But in many other problems, the solutions are not explicit. For example, sine of y plus log of the tangent of y plus x equal to 3, right? There is no way you can solve it explicitly, but maybe numerically you can do something about it that we will not really discuss it. So the bottom line is that in linear equations, you can always find explicit solutions. That is not the case for nonlinear problems. Okay, there is no such a guarantee that you can find explicit solutions. So again, summary of the three things, and I'm going to try to demonstrate them mainly with examples. I'm not going to discuss the theory in any extent yet, but the theory that discusses existence and uniqueness is very different. The concept of having a general solution may not be applicable to nonlinear problems, and having explicit solutions is usually not the case for nonlinear equations. All right, so let me just briefly, because I said the first thing will be the existence and uniqueness, I'm going to go ahead of myself and discuss the existence and uniqueness of solutions for the linear ODE. So what we have is, we have the simple equation with some coefficient p of t, and the right-hand side is g of t, okay? So we would like to state a theorem that says when the solutions exist and are unique for this problem. So I'm reading, if the functions p and g of time, right, of the independent variables, are continuous in some open interval that contains t equal to t0, that's the initial time, then there exists a unique solution y equal phi of t that satisfies obviously the equation in some t within this interval alpha to beta. Bottom line, what I want you to pay attention is, the theorem says if the functions p and g are continuous in some interval, then there is a solution within some subset of that interval. That's all. All right, so if you have some functions that they don't have discontinuities in an interval, you can guarantee with this theorem that not only there is a solution, but it's unique. Okay? So, and by the way, for this particular problem, I can write the solution right away, because here's the solution, and I want one of you to remind me this very general solution, how did we get it? We discussed this in the earlier lecture. What was the method? I see a mu there, so obviously one of the methods that would derive it requires some mu. So what was that mu? The integrating factor, right? So the idea was we multiply the differential equation with mu, and then we try on the left-hand side to get d over dt of mu times y, all right? And so mu comes to be e to this integral of p of s ds. And you notice now I'm writing it in a more proper form, right? I put even limits, and I make the variable of integration to be s there, to be sure that you don't guys confuse it with t. So mu of t is this, okay? And the integrating factor gives you directly this solution. So obviously, this solution is the unique solution that this theorem refers to. All right, so let's move on now to nonlinear equations. Pay attention to the theorem. We suppose that f and the derivative of f with respect to y, remember f is the right-hand side, f and the derivative of f with respect to y are continuous in some open interval of t and y. So before we were only talking about the continuity of f, now we added the requirement that the derivative of f with respect to y is also continuous. Okay? Then, in some interval of around the initial condition, the initial time t0, all right, that is a subset of this interval from alpha to beta, there exists a unique solution that satisfies the initial value problem. So the big difference from the linear problem, it's this major task that says the derivative of f with respect to y has to be continuous in some interval, right, in y and t, which is this interval here. So not only f has to be continuous, but the derivative of f with respect to y has to be continuous. That was not the case. We didn't have such a thing in the linear case, and we didn't have it because the function here was really, you remember the equation? It was p times y, basically, and then some function of t, okay? Here we have a very general function, f of t and y, so we require the derivative of f with respect to y to be continuous. Now, I am going to highlight, actually, if I have time, at the end of the lecture, on how actually these theorems are proved, because the way they are proved may give you ideas on how you solve these equations numerically, okay? So if I have time, if I don't, you will read these things on your own. It's on the end of the slides, okay? And it's very educational because it contains ideas that you may have to use in other courses. So let me, so the conditions, by the way, stated from the theorem are sufficient but not necessary, okay? They're sufficient but not necessary. So for example, if we have continuity of f alone, not of the derivative, this, ensures existence of the solution but not uniqueness. And I will come back. I have another slide to discuss about this. So what you see here is if f and the gradient of f with respect to y are continuous, then there is a unique solution. All right? Not only it exists, but it's unique. All right? But these conditions are sufficient. They are not necessary. So let's do some examples. And all the examples actually I have for this section are equations that either you have done in the homework or they're already in the notes and we presented them in earlier lectures. You remember this equation? I think this is from the homework, isn't it? All right? So just so, I don't remember. OK, so you have an initial condition y at time 1 equal to 2. So basically, you have these solutions that you see on the right that satisfy the conditions that y at time 1 equal to 2. That's that dot there, OK? So effectively, these solutions exist for time t greater than 0. You agree? Right? If you look at the solutions, these are particular solutions, right? Will you agree with me that these solutions up there exist, that the ones that satisfy this exist for time t greater than 0? Right? They never become negative. So can you guarantee to me, actually, that the solution to this nonlinear equation exists and it's unique? So if we do not really compute this analytically, can you guarantee to me that the solution to this is, actually, this is a linear equation. What am I talking? All right, so this is a linear equation. OK? So tell me why the solution for this problem is exists and is unique, according to the first theorem. According to the first theorem, what needs to happen for the solution to exist and be unique? Remember, for linear equations, what's the only requirement? For linear equations, what was the requirement? Something needs to be continuous. What is that something? Guys, you make me go back and back and back. All right, so what does it say here? If the functions p and g are continuous, right? These are functions of time only. All right, so if the functions p and g are continuous. So look at this equation and tell me, for the solutions that, that satisfy this initial condition, so the ones that have t greater than 0, is p and g continuous in some interval around the initial condition? At what point the function p and g are not continuous? At the point 0. But you notice the solutions that we have plotted there, the ones that we did in your homework, either they exist for t greater than 0, right? That's what we did, or for t negative. OK? So the theorem basically guarantees that this initial value problem not only has a solution, but has a unique solution, and it's actually given by this particular equation that you see there. Now, I am not going to change in this particular case the initial condition, but if somehow, I give you no, can you give me one initial condition where somehow the theorem will fail? Y at 0 equal to something. Can you see that? Because then you will need a subinterval around where? Around time 0, and around time 0, P and G are not continuous. You see that? Yes? Yes? All right. How about this nonlinear equation that we also did in the lectures and maybe in the homework as well? And I remind you, in this case, the solution we looked was for initial condition y at 0. That's the black line. Y at 0 equal -1. Okay? So that's the black line. And actually, we derived the analytical expression for this. So obviously, there must be some solution. But this problem is nonlinear. So tell me, according to our theorem for nonlinear ODEs, if this particular problem has a solution and if that solution is unique. So what we will need to actually prove to say something about the existence and uniqueness of the solution. You know, I can come next to you here and close my eyes too, but that is not going to help anybody because I see some people with the eyes closed. Must be the lighting from my laser. Okay? So look at this equation. It's a nonlinear equation. What do we need to actually show to guarantee that this particular problem with this particular initial condition has a unique solution? So, right, so we're going to have to prove that f and the derivative of f respect to y are continuous in some interval of t and y around time 0 and around y of 0 equal to -1. Everybody can see that? So if you actually take the derivatives, this is what it comes from taking the derivatives. So what is the interval where these derivatives are not continuous? At what point suddenly these derivatives blow up? F and the derivative del f over del y blows up. Say it again. Y equal to 1, and you notice my solution actually doesn't go up there, right? So my solution, the initial condition is y of 0 equal -1. So obviously around time 0 and around the value of y that is -1, both of these derivatives are continuous, so there is a unique solution of the nonlinear ODE in some subinterval there. Can you see that? Can you look at the picture and tell me one initial condition that somehow will not give you will not give you a solution, or it will give you multiple solutions? And actually, I can see them visually. Looking at that picture, I can see somehow two solutions somewhere. So can you give me one initial condition that somehow the theorem will not apply, and effectively because there are two solutions? Plus, minus. So what initial condition will I need to, and I don't have, don't even know how to zoom further and further to point you to a point, but it's there, it's in the center. So what initial condition will you put for somehow the theorem to fail? Y at 0 equal to? Equal to 1, because then you will need to find the subinterval around to 1 where f and del f over del y are continuous. But you cannot do this because around at y equal 1, this thing blows up and this thing blows up. And you can see actually when you compute the solutions for initial condition y of 0 equal to 1, actually there are solutions, but there are two solutions. You remember the way we got this problem to work? We got a quadratic equation for y, and it comes out for y of 0 equal to 1, you get one solution that is something plus that square root, and another solution that is something minus the square root. You get two solutions, and here are the two solutions. You see that straight line going up, and then another line going down? You get two solutions. All right? So the theorem fails. I mean, cannot say to you that there is a solution, and certainly cannot say that's unique. And the way to see the failure is to notice when you compute actually, you try to solve this ODE, to compute two solutions, and obviously the theorem only refers to existence and uniqueness. So this is the solution, by the way, that we compute. This is the solution corresponding to the black line, all right? So it's a unique solution, all right? So the theorem works very nicely. And the other case that I mentioned is a solution that looks like this, 1 plus minus the square root. So there are two solutions, two branches, two different solutions. And actually, you know, the interesting thing, right, with nonlinear equations, differential equations, is that you get multiple solutions. So that's why you have, you know, solutions that are stable, solutions that are metastable, unstable. So it's very important to know exactly what solution you get. So this is not math for mathematicians. This is math for engineers, because this type of problems, you can get them from mechanical vibrations to fluid mechanics to other type of instabilities in engineering science. All right, how about this problem? Somehow I give you the solutions, and I give you the f and the gradient of f. Can you tell me if this problem has actually, this is trivial. Look at it. Look at the gradients there and f, and look at the initial condition, and tell me if this problem satisfies the theorem, having thus, you know, a unique solution. You notice the initial condition here is y at 0 equal to 0, all right? And if you put y, so obviously for the theorem to work, these things need to be continuous in an interval around y of 0 equal to 0. So if you put y equal to 0, what happens to these things? What happens to that? Blows up, right? So it blows up, and the theorem indeed cannot tell you about a unique solution, because the problem actually has two solutions. And I can tell you, if you actually go and solve it, the two solutions come to be y equal to plus minus the square root of 3/2 of 2/3 of t. And you can see the two solutions actually that you get for this particular initial condition. So can you tell me what initial condition you will put again on this problem to make the solution unique? What initial condition will actually give you only one solution? Because what you see here, right, are solutions, okay? This particular case that I'm concentrating is y of 0 equal to 0. So what condition you would like to have what would you like to have for y of 0 to get a unique solution? Give me one number. 1, 5, 25, 65. Not to be at 0. Okay? And I know you're not going to believe me, but if you solve that ODE with initial condition equal to 5, right? So just by changing that number, the solution will change drastically, because it will not give you these two solutions. So immediately you can see the solution that you get, it doesn't only depend on the right-hand side that you have there, it also depends on the initial conditions. You change the initial conditions, the solution changes day and night, right? This doesn't happen with linear equations, it happens with nonlinear equations, okay? It's all in, you know, what is happening in your neighborhood, okay? And in our neighborhood here, this blows up, and because it blows up, you get two solutions. You could have gotten no solution at all, but you're lucky to get two solutions. All right. Let's do this problem, and I don't think we have done this. Maybe we have in an earlier lecture. So y prime equal y squared, right? So obviously that's a nonlinear problem. I put a condition y at 0 equal 1. So that intersection point that you see there is initial condition, and this is the solution that you see here, okay? So according to the theorem, looking at f and the derivative of f, do I have a unique solution to this nonlinear problem? Don't look at the pixels or anything. Just look at this and the theorem and the initial condition, y of 0 equal to 1. Do I have a unique solution for this problem? Yes or no? Yes. I heard a yes? All right. So I heard a yes. So indeed, there is a unique solution because this around y, an interval around time 0 and an interval around y of 0 equal to 1, okay? They're continuous. But let's look how the solution comes to be, okay? So when you calculate the solution, actually the solution comes to be 1 divided by 1 minus t, and that solution blows up at t equal to 1. And the theorem doesn't tell you anything whatsoever about what's going on at t equal to 1. Do you see this? Somehow, right, the solution goes up to infinity at t equal to 1. The theorem doesn't say anything because the theorem guarantees existence and uniqueness of solution where? On that little tiny interval around the initial conditions, all right? So how big that interval is going to be to say with confidence that this has a unique solution, you just don't know. All right? So you just don't know. Of course, you know, the idea here is because, you know, if you can guarantee a solution, let's say, on this interval, maybe you can start pushing it further and further, trying to keep moving the window with different initial conditions. And in that case, certainly, you will find this discontinuity. But my point here is there is a discontinuity in the solution, and it's hidden. Is there anything in y that tells you that at t equal to 1 you have a discontinuity? Nothing. So, I mean, I trust that this solution is correct, right? Right? So I trust that this solution is correct, but there is nothing there that says that we are going to get any discontinuity in y. All right. So we talked about this interval, so I am not going to go back. So let me make, so you remember we said there are three major differences between linear and nonlinear equations. One was with the two theorems for existence and uniqueness. They were very different. The other thing we said is that in linear equations, we get these general solutions defined with some constants of integration. In nonlinear equations, even if you have a general solution with some constants of integration, there may be other solutions that there is no way you can get them by plugging in different values to these constants. And here is one example. You will agree with me that this problem has this solution, minus 1 over t plus a constant. You can actually differentiate it and, and verify that there's no typo there. So I trust that that's what you get. Can you give me okay, it says there, so the answer is there. But can you agree with me that y equal to 0 is a solution? Right? If you put y equal to 0, left-hand side 0, right-hand side 0, it's obviously a solution. And I'm asking you, if you do integration, right? This is a separable equation. You can integrate and you get that. How do you get y equal to 0? What constant do you put in to get y equal to 0 at all times? Huh? Infinity. He's very smart now. He's trying to argue with me that if we put infinity, we'll solve the problem, all right? Now you make me think about it, okay? So, but generally speaking, right? So if we don't accept the infinity as a constant to be an option, okay? To be an option, you can see you cannot get with a constant of integration. Actually, I am not even quite sure when you integrate, can you put a constant of integration to be infinity? Okay? That's your homework, okay? Think about it, okay? I think that must not be acceptable. All right? So the bottom line here is you may have solutions that you cannot get from these general solutions, which effectively means you may not have general solutions for nonlinear problems. All right? Just so I can finish, all right? So for linear equations, we said there is an exact solution, right? And for linear equations, this is the exact solution, okay? Now, if you ask MATLAB to solve for you, and I really want you in like the next homework, I really want you for every problem to actually use the MATLAB solver to compute for you the exact solution to your equations. But if you ask MATLAB to solve it, generally MATLAB is not a symbolic programming language, right? It's not going to be able to take for you what the function g is and what the function mu is and perform a symbolic integration. You can do this with Mathematica. Actually, back the old days when I was a graduate student, one of the big things that had happened is there was a program that was called this company doesn't exist anymore. Not Maxima. There was a symbolic language that you would be able to actually put equations in terms of symbols, right? Second derivative type in this, and then you can even do expansion, you know, give me a Taylor series expansion of this and that. So the symbolic language things can actually do this integral for you analytically if that integral exists. And you can do this with Mathematica. What MATLAB does is actually it uses quadrature rules to calculate this integral. So keep that in mind when you're asking MATLAB to compute a solution. It doesn't necessarily spell for you an exact solution. It spells a quadrature that may look in a very primitive sense like this summation. So if you split the interval from 0 to t in small pieces, you approximate the area under the curve with little rectangulars, and this is what you write here. But I want to assume that it does better than that using a sparse quadrature. And if it happens that this integral exists actually analytically, this quadrature gives you the exact answer. So even though it's a numerical approximation, if this integral exists, it will give you the exact answer with a proper selection of these subdivisions that you do there. So again, what you may perceive as an exact solution from MATLAB, it may be, even for a linear equation, may be a numerical approximation the way that you see here. Just so I can finish, right, that nonlinear equations is a very new territory for everybody, because if I change the equation, what you get actually can be extremely weird things. So here is an equation, okay? Y prime equal y cosine of x over 1 plus 3y cubed. This is how the solution looks like. And I mean, if you're an engineer or a physicist and somebody tells you this is the potential, the electromagnetic potential or pressure or something like that, you look at it and you say, goodness, something is going on here. I have all of these modes with some periodicity, and then I have another periodic solution that looks like sines and cosines. Where all these things come? Well, they come because nonlinear equations hide a lot of what's going on in the world, okay? So small nonlinearities are sufficient to give you miracles when it comes to the solution to these problems. Okay, so let me go to slide 135, okay, and discuss, so we can say something about stable modes and unstable modes, discuss some simple systems that they're called autonomous systems, right? And some of you that will work in dynamics and robotics, you will have to play with this type of equations, but also a lot of the literature goes with the name population dynamics, because the way you measure population of animals and humans etc., use the same sort of equations that you will see shortly. So first, what's an autonomous system? If you look at the equation on the right-hand side, f of y, and there is no time t, then we call this system an autonomous system, okay? If there is no time t explicitly, that's an autonomous system. And the simplest, since we're going to refer to this population dynamics, the simplest autonomous system is one that is trying to model exponential growth with a growth rate r. R is positive. The solution of that system obviously is y0 e to the rt, right? So you can appreciate why r is the what governs the growth rate, okay? And the solution looks like this. All right, so an exponential growth problem for an autonomous system with a growth rate r, it has solutions that looks like these lines. And the only thing I want you to remember is, obviously, as t goes to infinity, it blows up, right? The population increases to infinity. So obviously, this is not a very realistic model for population dynamics. So we will have to actually do something and improve this model if we want to model the population of animal or humans, okay, or something like that. Now, if r is negative, all right, actually, I don't have it. I thought. So if r is negative, what is going to happen? Can somebody tell me? So you are going to have an exponential decay, basically, and these curves will be, rather than going up, will actually go to minus infinity. Actually, what am I talking about? If r is negative, what's happening? The population will die, okay? So this whole thing goes to 0. All right, so let's start improving this model. And we're going to improve this model by the equation that you see on the bottom that is called in the literature the logistic equation, okay? So let's concentrate directly on this equation. So rather than having a growth rate r that is constant, now you notice that the growth rate is r minus alpha y, where both r and alpha are positive numbers. So the growth rate is, rather than being constant, is r minus alpha y. So it depends on the population itself. So you can see if y is small, all right, if y is small, then the growth rate is r. That's what we had before. But as y increases, the growth rate decreases. And as y is very big, the growth rate is what? Is negative. Okay? So before I actually, so this model actually is way more realistic than having an exponential growth or a decay to 0. So the only thing we have done is we took a linear function to represent this growth rate. So from r, we went to r minus alpha y. Before I do anything, right, can somebody tell me what type of solutions? Do you think the solutions will change here? So we basically, this what it says is, as y grows, right? Before, you remember we had exponential growth, says as y grows, this growth rate, the coefficient inside the parenthesis, then becomes negative. So effectively, it says the population cannot go to infinity. And what do you think, eventually will go if it doesn't go to infinity? So, if the population grows, can it grow forever? What happens to it? What do you think? And actually, you can even look at this equation here. Do you have any equilibrium modes, any stable, we cannot say stable or not, but do we have any critical points for this equation where the change of the population is going to be equal to 0? Y equal r over a, and y equal to 0. Can you see that? So there are critical values of y. One of them is y equal to 0, and the other one is y equal r over a. And the y equal to 0 is going to turn out to be an unstable mode. So if you are close to y equal to 0, you will try to escape from there. But the mode that is y equal r over a, we will see that's a stable mode, and the solution will try to approach that critical point from above and below. All right, I don't have time to actually go through all the details. Let me just, they're very elementary. So the first thing we do is, rather than having this abstract parameter, alpha there, in the literature, they write a logistic equation as dy over dt. They move r outside, and inside they're going to have a divided by r, right? A divided by r, and they call this 1 over k, where k is what they refer to as the carrying capacity of the population, and you will see why when we plot the solution. I mean, you can actually see that the critical point this way is going to be y equal to k, all right? So it's just a reformulation of our logistic equation instead of a using a k, all right? And it's easier to remember actually this equation like that, okay? It's my constant growth rate, if you like, times 1 minus y over k. All right. So if you do this direction field, this is what you get, okay? So if you go and you evaluate the right-hand side the way you have done in the homework for different values of y, this is what you get. So I want you, without doing any algebra, no calculations, look at that picture and tell me, summarize for me all the nature of the solutions here. So if you start with some initial condition anywhere, let's say in this case, k equal to 10, all right? So this is one critical point, and y equal to 0 is another. So if you start anywhere for y0 between 0 and 10, can you tell me what happens to the solution? Looking at this, direction field. So anywhere from y0 between 0 and k, what happens to the solution? It goes to k. So everything goes to k. And you notice, even if you start infinitesimally close to y equal to 0, it escapes from y equal to 0. So even though y equal to 0 is a critical point, right? You can see there, it's an unstable point. It doesn't want to be there. Can you actually think the only way to stay at y equal to 0, what that way will be? What would be the only way to stay at y equal to 0? If you start exactly with 0, you will stay at 0. All right? But if you start with 0.00005, you will escape and you will go to k. Okay? So what I have in the notes is an elementary discussion on how actually you can figure out the whole nature of the solutions without actually solving anything, just by doing simple calculations, working with the right-hand side, okay, and figuring out the critical points and the nature of the solutions, including, is the solution increasing, right? I mean, if somebody asks you to compute if the solution will increase or not without actually computing the solution itself, what will you evaluate to figure out if somewhere the solution increases? Look at this. If I am asking you at a given point, let's say, in y, right, and at a given time, there is no time dependence here, but if I ask at a given y to tell me if the solution will increase, what will you evaluate? It's there. So if I give you a given y, how do you know if the solution there will increase? You will evaluate what? This is the slope of y, so what you will evaluate is this, right? And if I ask you, is the solution going to be convex or is it going to be concave? What will you do at a given point? You will evaluate the second derivative of this and see if it is positive or negative, without ever solving the differential equation. So if you actually do all of this, all right, and again, they're in the notes, you will see if the function f of y, all right, for this logistic regression problem, looks like this, okay? So immediately you can Can you tell me from 0 to k, if I give you the solution y between 0 and k as my initial condition, will the solution increase? Will the value of y increase? This is the value of f of y. It looks like this. If I plot this quadratic, this is what I get. Between 0 and k, is y going to increase and y? It will increase y because f, that is the slope of y, is what value? It's positive. And this is indicated in the graph with this arrows pointing to the right, saying it will increase. The value of y will increase. All right? And how about for values of y greater than k? The slope is negative, so y will decrease. So you put an arrow to the left. So can you immediately, by looking at these arrows, immediately conclude actually that the point y equal to 0, it's unstable, because if you are close to y equal to 0, the value of y will increase. But if you are anywhere either to the left of the value k or to the right, what will you do? You will go towards the value k. It's a stable mode. Yes? So the idea here is, right, you can learn a lot of things. And it's not all manual calculations of integrals and solving differential equations. You need to be able, without doing anything, just by plotting the direction field or looking at the right-hand side, to say something about the nature of the solutions. And here, actually, we have said everything. And actually, let me ask the following. How will you evaluate for me the curvature of the solutions at a given y? So if the curve will be upwards, curved upwards or downwards. So we said we are going to have to calculate what? The second derivative of y. And the second derivative of y is what derivative of f of y? It's the first derivative of f of y. So can you tell me the interval where y, it will be convex, and the interval where y will be concave? Look at this plot and tell me the interval. So you know, what happens to the slope of f of y from here to k over 2? What happens? Increases. So the curvature in that region is expected to be what? Positive. It's going to be, the function is going to be convex. And from k over 2 to k is going to be concave. And actually, you know what? The miracle of doing this reasoning, it actually gives you solutions that they seem to actually obey all of the above. Look at this, right? So from above, the solution goes asymptotical to k. From below, it goes asymptotical to k. You escape from this. Can you look at this? Look at the bottom line. Can you see that, that it's first from 0 to k over 2, that it's convex, and then it becomes concave? Can you actually see that? We didn't really solve any equation. We just argue by looking at the slope of f of y, that up to k over 2, it's convex, and then becomes concave. Because you remember y, we're interested on the solution y, all right? And dy over dt is f of y. We in this, so actually this is what I have done. And if I can find the slide, all right? How will you, let's do the following thing. How will you take the second derivative with respect to t? No, you know, because everything is a function of f, so you will take first the first derivative of y with respect to t, which is f, all right? And f is a function of y. So how will you differentiate f as a function of y? You will have f times, is the chain rule. How will you do the chain rule to calculate the second derivative? You see that? Okay? So basically, you have the derivative of f times f itself to give you the curvature of y of t. Okay? So if you put all of this together, all right? And again, if you can read them, you actually, and there is the calculation that we just discussed it, okay? So this is what you have here. If you want the second derivative of y with respect to t, will be basically dy over dt is f, so it will be the first derivative of f times dy over dt, the chain rule. Okay? And so we get basically the whole solution. If you have the direction field, you can actually draw them. Obviously, this is qualitative, it's not quantitative, but if somebody comes and tells you the solutions look like that, to me, that's more important information than somebody giving me an equation, right? Because if you give me an equation, then I have to plot it. I need a computer. This I can do it in a piece of a napkin and say, this is how the solutions look like. And so if you want to actually solve this equation, obviously, so let me just directly give you the solution. So this equation you can is separable. So you can move all the y's on one side, all the t's on the other side. And if you split this, because you have two y terms, if you split them in like this, okay, you can actually integrate each term separately. And the solutions actually are given. Let me just go directly. The solution is what is given on the bottom. Okay? Looks like this. You notice if t equal to 0, right, this becomes 1. y0 and y0 cancel. K and k cancel. So y equal to y0. And what happens when t goes to infinity? When t goes to infinity, this exponential term goes to 0. And y goes to where? To k. And actually, it comes up that this solution is actually the correct solution if you're below k, or if you're above k. All right? You get exactly the same sort of solution if you're above or below k. And actually, the proof is on this slide if you want to do the heavy calculation. All right. So again, we have one stable mode and one unstable mode. Let me, I'm going to do, if I can only find it. So what have I done in this equation, by the way? This looks a little bit different from before. You know what is different? What is different? There's a minus sign there. All right, so it's a minus sign. So if you try to actually discuss what's going on with this equation, it comes out that you get the opposite thing. If you are below this value t, everything goes to 0. If you're above, you go to infinity. So this is an unstable mode, and the 0 becomes a stable mode, okay? And the question is, can you do something to actually correct that above the value of t, this does not go to infinity? And here is one improvement of that model. And that improvement is, come on, show to me. There is the improvement, okay? So if you have an equation modified like this, okay, then if I can finish, the k value becomes a stable mode. The t becomes an unstable mode. The 0 becomes a stable mode. But notice the solution does not increase exponentially. All right, the solution does not increase exponentially. So I will see you after fall break, so you have good time. All right, and if you have any questions about the homework, email me.